So here is the hardware design of SCANC at the gate level. I'm using a hardware design language called CUPL, which was introduced by Atmel, which is now part of Microchip, back in the early 80s. The latest version of the tool I'm using here that you're seeing is from 1998. So this is really a retro design and retro hardware design. There is no doubt about that. The beginning of the file, I will explain to you both the design and the grammar of this design language. It's simple enough that we can do both at the same time. We start with the title, and then we specify the device we are going to use, the particular CPLD. I'm going to use an ATF1508AS, which is a large CMOS 5-volt CPLD. I'm specifying here that it should be in-system programmable, so the tool will reserve some of the pins for in-system programmability via JTAG cable. There is some commentary, and then we have to specify the inputs, the outputs, and the so-called buried states. In a CPLD, all the logic is associated with a pin. Even if you don't use that pin for I/O or input-output, but you use the logic associated with it, you have to declare that in this pin node declarations here. Well, let's start from the inputs. The first input is the pixel clock, 25 point something megahertz that come from the oscillator. Then we use 8 pins here for these bits here called character byte from 7 to 0. So these 2 little dots here represent CB7, CB6, CB5, and so on until CB0. And then we use a field declaration to refer to all 8 bits with a single word, this new char byte. These inputs here, these 8 bits, are basically the output of the character memory that is then loaded into SCANC's shift register, like we talked about in episode 2. And then we have the outputs, which are basically the 3 VGA signals that go to the monitor. The horizontal sync pulse, and here the vertical sync pulse, and the RGB signal. Usually it's 3, but we will wire all of them together because it's just a black and white video signal. Then SCANC also generates the cavia clock, which is 1/16 of the pixel clock. So this is also an output of cavia. And then we have a number of internal variables which are latched. They are latched into flip-flops. That's why we have to declare them. We have the detectors here, like the horizontal front porch detector, the horizontal sync pulse detector, and so on and so forth. Also for the vertical side of things, we have all the detectors for us to know where we are in the scanning cycle, whether we are in frame or in one of the porches or in one of the sync pulses. Then we have 4 states here, which are used for a 0 to 15 counter, 16 counter, and that's basically to divide the pixel clock by 16. Actually, this is 16. We are dividing it by 16. And we do that because that's the way to generate the cavia clock and the shift register clock, which I will show later on. We have some more internal states. These are the flip-flops or the states used for the horizontal counter, which counts to 800. And then we have the same thing for the vertical counter, which counts to 525 lines. Both of them require 10 bits. Now, these are the declarations of the shift register states. I am declaring 7 here. And we might ask, well, it's an 8-bit shift register. Why are you declaring only 7? It's because number 8 is here, is the RGB signal. The least significant bit of the shift register is an output. It goes to the monitor. This is a handy declaration when we specify the workings, the functionality of the shift register. I will come back to it later on, this one as well. And this declaration here is, you don't need to understand this. This just avoids for me the need to put external pull-up and pull-down resistors. By declaring this pin keep on the CPLD, we do it internally, which is handier. Okay, so now here we have the clock divider, which will divide the pixel clock by 16 and by 8. There are 4 states, one per flip-flop. This .t extension here identifies a toggle flip-flop or a T flip-flop. If you don't know what it is, you can look it up on Google, a T or toggle flip-flop. And this is the standard specification of a counter based on a toggle flip-flop. The input of each flip-flop is the output of the previous ones ended together. This ampersand is a logical end in couple, and the first one is just a binary 1. And then we specify the clock via this .ck here. We specify the clock for all 4 flip-flops, and that will then be the input pixel clock. And then we specify a clock enable term for all 4 flip-flops as well. And what this is basically doing, it's saying this clock can tick, and I can move with the states in this clock divider only if I am not in any of the porches and I'm not in any of the sync pulses. Because remember, these are the detectors for those other parts of the scan. This is let me see, this is the horizontal front porch detector, this is the horizontal sync pulse detector, the horizontal back porch detector, the vertical front porch detector, and so on. And they are negated. The exclamation mark is an inverter, it's a not, logical not, and the ampersand, as I said, is a logical end. So this clock enable here will only be valid, will only be asserted when you are in frame and not in any of the porches or sync pulses. And the reason is you're only printing things on the screen when you are in the frame. So if you count here on this clock divider while you're not in the frame, the whole thing will lose sync. Now, the cavia clock is special. It's taken as one specific state of this 16-state counter. So only when the state of the counter is 0, 0, 0, 0, remember this is a not, so this will only be asserted when all 4 states here are 0. So when that happens, then the cavia clock will tick, and the effect is that the cavia clock will be 1/16 of the pixel clock. And it will only tick when you are in frame and not in any of the porches or sync pulses, because this is a clock enable term. All right, now we have the horizontal counter. There are 10 states, H9, H8, H7, and so on. They are specified as T flip-flops. That's the .T directive. And this, again, is the standard way of constructing a counter with T flip-flops that you learn at university. If you don't know it, if you're not familiar with it, you can just look up online binary counter with T flip-flops or toggle flip-flops. The clock is then the pixel clock as well, but now we have a new term for all of the states. That's the asynchronous reset. So this term will reset the whole thing asynchronously. Let me beautify a little bit the layout. And if you look at what is in here, remember the exclamation mark is a not, and the ampersand is an end, a logical end. So the asynchronous reset will only be asserted when H9 is 1, H8 is 1, H7 is 0, H6 is 0, H5 is 1, and so on and so forth. So if you translate what I just said in binary, if you translate that to decimal, you will get 800, which is the maximum count of the horizontal counter. So when the counter, these states here, the H or horizontal states, reach 800, they will asynchronously reset the counter, and the counter will go back to 0. That's basically what it's saying here. Now we have the detectors, and the detectors work on the following basis. I am using D flip-flop or data flip-flop. You can look it up online as well on Google, D flip-flops tutorial or something, and you find it. It's quite simple. The input of the flip-flop is a binary 1 or a true, but it is only clocked in on this term here. So this term is being used as the clock of this flip-flop, and so the flip-flop will only clock and latch this one. This one will only be latched on the output of the flip-flop when this term is asserted, when it's 1. And if you translate the binary here, say 1 0 1 0 0 0 0 0 0 0, this is 640, and that's the end of the frame, or the beginning of the front porch. So this one will be latched onto this output, HFPD, only when the front porch begins, and that's why this is a horizontal front porch detector. And it will reset itself asynchronously once you reach this number here, which if you translate from binary, it's 656, which is the beginning of the sync pulse. So this signal, horizontal front porch detector, will be 1 during the front porch and 0 in all other counts. Now the same logic is applied for all the other detectors as well. The input of the flip-flop is a 1. It gets latched on this term, which works as the clock term, and in this case it's 656. So when the front porch detector is reset, the horizontal sync pulse detector is set. The 1 will be latched onto the output, and it will be reset at 752, which is the end of the sync pulse. And the same thing here, the back porch detector will latch 1 at 752, and it will reset itself at the end of the count. It's quite simple. Sorry for the formatting mess here, I will correct this later. Now we have roughly the same thing for the vertical part. It's the same thing. We have a 10-bit counter using toggle flip-flops. The clock now, however, is not the pixel clock. The clock now is a term based on the horizontal counter states. When the horizontal counter states reach 799, which is the maximum count for the horizontal counter. After that it's 800, and then it will reset itself immediately, asynchronously. So when the horizontal counter reaches its maximum, which is 799, it will have completed the line, and that will then clock the vertical counter, which should increment on a line basis, not on a pixel clock pulse basis, but on a line basis. So that's why we do this here. This guy will count every time the horizontal counter reaches the end of a line. That's the nature of the vertical counter. And once it reaches its own limit, which as we've seen is 525, it will asynchronously reset itself back to 0, and the whole thing will start again for the next frame. And then we have the same count, well, not the same counters, but we have counters of the same nature, detectors for different values, but essentially doing the same thing. There is a detector for the front porch, a detector for the sync pulse, and a detector for the back porch. All of them will latch 1 during their respective periods and will reset themselves asynchronously when the counter leaves the respective period. Now the actual output, the vertical sync pulse, is just the inverted version of the vertical sync pulse detector, because this is positive high, but the vertical sync pulse is supposed to be positive low, so I just invert it. And as a matter of fact, I forgot to show you this, but there is the same thing here with the horizontal sync pulse. It's just the negated or the inverted version of the horizontal sync pulse detector. This is positive high, and the horizontal sync pulse is active low. The final thing is the shift register, and here I'm using those field declarations, which save space. Instead of writing this 8 times for each one of the bits, I'm writing it for that field declaration called shift register, and the effect is to apply this logical equation here for each of the 8 bits. So what this basically is saying is the following. Remember that on the Cavia clock, a new byte from character memory is parallel loaded into the shift register. And then for the next 8 clock cycles, it's supposed to be shifted out to the screen via shifts to the right. So when the Cavia clock is on, a new character byte is parallel loaded into the shift register. And then you have this term here, which is a logical OR. The hash is a logical OR. And then you can specify the other condition. When the Cavia clock is not active, then you should just shift everything to the right. That's basically what it does. It specifies that on the Cavia clock, the shift register is parallel loaded with a new byte all at once, all 8 bits at once. And outside of the Cavia clock, when the shift register clock is clocking, it will shift the contents of the registers one step to the right on every shift register clock. Now, what is the shift register clock? It's this here. It's .ck is the clock, and I'm just taking state S1 of our clock divider. Now, if you go back up, here is the clock divider. It's basically a 4-bit counter, and I'm taking this state here, S1. Why? Because if you take the one before the least significant bit, the frequency with which this state is going to toggle will be half of the frequency of the clock divider. So this S1, if I use it as a clock, it will be 1/2 the frequency of the pixel clock, which is exactly what we need for the shift register clock, as we've discussed in episode 2. And then in addition to that, I am inverting it. And the reason I am inverting it is to keep the phase the same. If I don't invert it, S1 will be 180 degrees out of phase with the pixel clock and the cavia clock, and then nothing will work. So I'm taking S1 for the frequency, and I am inverting it to get the phase right. So when one of these clocks is high, all the others are high too, instead of being opposite. That's about it for SCANC. So let's now go test it, fetch the oscilloscope, and test all the outputs to make sure that all the timings are right. This is my test bed. I'm using a WinCUPL logic analyzer hooked up to the pin headers of an Atmel development board where SCANC is placed. I can also program SCANC in there, not only use it. This development board has a 2 MHz clock, which I will use for system clock. The value is not correct, it's not the one that's going to be used at the end, but we can scale all the timings and still get a very reliable test. We are going to first test the cavia clock, which is an output of SCANC to cavia, and it should be 1/16 of the pixel clock, and it should be withdrawn during the porches and the sync pulses, and that's exactly what you see there. The cavia clock in yellow is withdrawn around the vertical sync pulse in blue, exactly as it should be. And if we zoom in on that a little bit more, we can even see the spaces in which the cavia clock is withdrawn during the horizontal sync pulse and porches as well. Now let's measure the frequency of the clock. I'm using the cursors A and B to probe the period of the oscillation, and then you can invert that and get the frequency, and we get 125 kilohertz, which is exactly 1/16 of 2 megahertz, as it should be. So the clock is just fine. We can go and measure something else, and what we are going to measure now are the horizontal and vertical sync pulses. We are going to measure 2 things, the frequency and the length of the pulses. Both have to be right. We will start with the length of the horizontal sync pulse in yellow. I'm using the cursors there, and we get a length of 48 microseconds. That's bang on. That's exactly right. You should not content yourself with values that are not quite right, like a half a microsecond more or less. Don't think that this is noise. It's not. Those values should be bang on right. Now we are going to measure the length of the vertical sync pulse in blue. I'm using the cursors again, and we get 0.8 milliseconds or 800 microseconds, which is also bang on right. And as a bonus, you can see the little horizontal sync pulses in yellow, and you can see that 2 of those fit into the vertical sync pulse exactly. And that's exactly how it should be. Now moving on to measure the frequency of the sync pulses, both horizontal and vertical. We will start with the horizontal in yellow, using the probes again, and we get a period of 0.4 milliseconds. And that's exactly right. That's the frequency with which we should have the horizontal sync pulses happening. And finally, the frequency of the vertical sync pulses, also using the cursors, and we get a period of 0.210 seconds or 210 milliseconds, which is also bang on. So SCANC is ready to go. Everything is looking fine. Join me for episode 4, when we will be going over the design of cavia, which is a little more complex but quite interesting, and we will be testing cavia as well, just like we did SCANC today. So see you then. Take care.